Welcome again, ladies and gents, to another flipped lesson. Today our focus is going to be on understanding what occurs when a phase change is taking place. This covers pages 529 to 533 in your text. Let's go ahead and get started. This guy here is what we call a heating and cooling curve, and he's going to be the focus of our class over the next couple of days. And what these heating and cooling curves do for us is they give us a visual representation of different changes in the state of matter. So if we look at our axes, we can see that we've got temperature increasing on the y, and we've got heat energy being added across the x. And so as we change our heat energy, you can see that it specifies where we find the different states of matter. So we see solid on the lower temperatures, liquid in the middle temperatures, and gases at the higher temperatures. And in between the temperatures, we can see that's where we have state changes occurring. So between our solid and our liquid, we've got freezing and melting depending on what direction we're moving on the flat line. And between our liquid and our gas, we've got condensation and boiling happening depending on what direction we're moving again. So this guy gives us a nice little roadmap where we can see what state of matter we have and what state of matter we're going to when heat is added or removed in a state change situation. Now, we learned different words for the state changes earlier this semester. So the only thing that stinks about that heating and cooling curve is it doesn't necessarily use the words that we've learned already. It throws a couple of new state change vocab words at us. Now, good news is the state of matters are still called solid, liquid, and gas. It's just these in-between words that we're going to get new ones for. So when we're going between a solid and a liquid, we learned that that's what we call melting. Now, this new word scientists throw at us is the idea of fusion. So from now on, when we talk about going from a solid to a liquid, we're going to call it fusion. The reverse, we called freezing. We're going to call it solidification. Now this one doesn't make too much of a stretch because it's turning into a solid, so it's solidifying. So that one's not too difficult. Now we talked about going from a liquid to a gas as evaporation, and we're just going to shorten that to the word vaporization. And then going from a gas to a liquid is what we now call condensation, and that word stays the same. So these are going to be our new words that we use when we talk about state changes. Now, going from a solid to a gas is still called sublimation, and going from a gas to a solid is still called deposition, but on our heating and cooling curves, we really don't use those. So these are the four main words that we need to focus on. Now, what we're going to learn to do with that heating and cooling curve is calculate the amount of energy we need to do a state change. And so these words all have a specific energy amount associated with them in order for the state change to take place. And that's represented by this little delta H, and that H is what we call the enthalpy of something. So when we're looking at each of these state changes, they all have their own enthalpy. So if, for example, we were looking at fusion, we would call that the delta H of fusion. And then in this blank, we would write the word fusion. All your delta H's are going to be defined as the amount of heat needed to do something to 1 mole of a substance. So if we're looking at fusion, we're going between the solid and the liquid. So the delta H of fusion is how much heat we need to melt 1 mole of that substance. And what you can see with this definition is we can just play fill in the blank. We can go ahead and we can replace the fusion with solidification, and then it would be the amount of heat needed to freeze 1 mole of a substance. We could do the same thing with vaporization and condensation. So we can represent all four of these state changes with their own delta H. So all of these things are represented with their own amount of energy. So let's go ahead and let's look at one of those energy amounts. And the energy amount we're going to specifically look at is going to be the energy amount needed to go between the solid and the liquid state. So if we think about a solid, we know that solids are highly organized and arranged. Okay, so when we're thinking about something like solid water, all of our water molecules are attracted to their neighboring water molecule through a hydrogen bond. And as we've decreased the temperature of that solid, these water molecules get locked, fixed into place, and so their intermolecular force is extremely strong, keeping them in this highly organized, compact structure. If we compare that to a liquid water, however, you can still see that we do have the intermolecular forces intact, But because we're now in this liquid arrangement, the organization is broken down a little bit. So the water molecules have freedom of movement to slide back and forth with each other, so they can start to make intermolecular forces with a bunch of different water molecules in different locations in that liquid. Where in the solid ice, they can only make an intermolecular force with the things that are directly next to them. So if we talk about the amount of energy we need to take to make this solid into a liquid, we call that the delta H of fusion, which is what you investigated in your lab yesterday. And that numerical value is 6.02 kilojoules per mole. So what that tells us is if we want to take 1 mole of ice and turn it into liquid water, we would have to input 6.02 kilojoules, which I know seems like a lot of energy, but it's really not that much. We can have this happen at room temperature all the time, as you see when you put ice out in just your everyday lives. Now, if we want to solidify that and go backwards, you can see the sign becomes negative, and that's super, super important. Because when we think about if we want to turn a liquid into a solid, we know that we need to go ahead and steal the energy from this substance in order to turn it from this unorganized liquid freedom of movement to this rigid organized solid structure. So since we're taking the energy out of that liquid to do that process, our sign becomes a negative value. So let's go ahead and let's go back to that picture and kind of talk about what's happening here. So when we think about where this is happening, this fusion and solidification process is happening right here on this first flat line. So if we're thinking about water, we know that water melts and freezes at 0 degrees Celsius. And what we can see is that during the process of melting and freezing, we're still putting energy in, but our temperature is not changing at all. The reason is because the energy that we're putting in order to, let's say, melt our solid ice into a liquid, it's not going into increasing the kinetic energy of the molecules. What it's going to is taking those intermolecular forces and weakening them. In our solid, it's a very highly organized structure, and in our liquid, that's broken down. So we have to put energy in order to take those intermolecular forces and weaken them so we can now have freedom of movement in that liquid state. So it's almost like it's taking the intermolecular force and loosening them up a little bit. So they're not completely broken, those intermolecular forces are still intact, but we now have freedom of choice per se to who the water molecules can go ahead and make an intermolecular force with. Now the interesting thing about this line being flat is it's denoting that our temperature is not changing at all. So what that means, if we think about this between the solid and the liquid, it's like a glass of ice water. So if I'm over here towards the solid end of my line, this means that I would maybe have a glass that's like 3/4 water and 1/4 ice. That temperature is still going to be 0 degrees Celsius. As I let it melt longer and longer along this line, and let's say I get to a situation where I've got 3/4 water and only 1/4 ice now in that glass, the temperature is still going to be 0 degrees Celsius because my temperature cannot change until all of my solid has been fully converted into a liquid. At that point, we can start to have the temperature of our liquid raise. So while you're in that state change area, your temperature remains constant until all of your solid has fully turned into a liquid. Now, if we go and we look at our next state change, which is between the liquid and gas situation where we're vaporizing and condensing, we can see that the amount of energy that we need is significantly more. So to vaporize a mole of water, we would need to put in 40.6 kilojoules of energy in. And to, I forgot to change these words. Oh, sorry, that word's okay. No, wrong thing. I forgot to change this word, my fault, kids. This should be condensation. Sorry about that. So we can see that in order for us to vaporize a substance, we would have to put 40.6 kilojoules, to vaporize water, we would have to put 40.6 kilojoules in to go ahead and turn it into a gas. And then to go ahead and condense this gas into a liquid, we would have to again remove those 40.6 kilojoules per mole because we're stealing the energy away from that gas to get it to turn back into a liquid. So it would be a negative value. So if we look at this chart again, we can see if we're talking about water here, this would be happening at 100 degrees Celsius. We can see that this line where our condensation and vaporization is occurring is flat again, but we're definitely still putting energy in to make this state change happen. So if we think about what we're doing when we turn from a liquid into a gas, we learned that in order for a substance to evaporate in the last chapter, we have to 100% break free of our intermolecular forces that are found in the liquid state. So this is going to require a significant amount more of energy because we don't want to just loosen those forces to allow these things to kind of move within the liquid. We want to completely break free of our forces to give us freedom of movement in the container that we're in. So breaking that intermolecular force is going to require a significant amount more of energy than just going ahead and loosening it up from the solid to the liquid. So it's going to require a much larger amount of energy to break those forces. And conversely, it's going to require us to remove a lot more energy to condense this back into a liquid and get those forces back intact. So on your Google form, I've got a couple of questions for you to consider about this video. The first thing we want to talk about is why does it take so much more energy to vaporize a substance than it does to melt the same substance? So I've thrown up the numbers for water up here for you to go ahead and think about that as you answer that question. The last thing I'd like you to think about is evaporation an endothermic or exothermic process? Remember, if you get questions, you can always swing by in the morning or shoot me an email. Have a great night, kids.